Hey everyone, and welcome. Today, we're going to metaphorically tear down a server and get right to its core. We're going to focus on the two parts that honestly matter most: the brain that does all the heavy lifting and the heart that keeps the whole thing alive. You ready? Let's dive in.
So here's the plan. First up, we're getting to know the server's brain, the CPU. Then we'll look at this big split, a tale of two architectures, really, that defines how they work. After that, we'll decode what actually gives a processor its power. Then we'll pivot to the heart of the machine, the power supply, and wrap things up by looking at how both of these parts are keeping up with today's crazy demands.
All right, first things first. Let's talk about the brain. We're jumping right into probably the most famous component in any computer, right? The central processing unit. You know it as the CPU.
You know, people call the CPU the brain all the time, and for good reason. It's a perfect analogy. It is the absolute command center. It's taking in instructions, crunching the data, and telling every single other component what to do and when to do it. Honestly, without it, nothing happens. It is the most critical piece of the whole puzzle.
Okay, so let's get a little more technical, but not too much, I promise. At its core, a CPU is this giant integrated circuit. And if you break it down, like we see here, it's really got three main jobs. There's the arithmetic logic unit, or ALU. That's the mathematician, handling all the numbers and logic. Then you've got this super fast memory called cache, and we'll definitely circle back to that later. And finally, you have the bus. Think of it like a data superhighway connecting everything together.
So now we know what a CPU is, right? But here's the thing. Not all CPUs are built the same way, not even close. Their fundamental design, what we call their architecture, basically creates this massive fork in the road for the entire processor industry.
Okay, so on one side of that fork, you've got CISC. That stands for Complex Instruction Set Computer. Now, the whole idea with CISC is to get tasks done with as few lines of code as possible. This makes the processor itself way more complex, but it can make life a little easier for the people writing the software. Then on the other side, you have RISC, Reduced Instruction Set Computer. This flips the whole thing on its head. It simplifies the processor by using only very basic instructions, which means the software has to do more of the hard work. Now, for what we're talking about today, server CPUs from Intel and AMD, they're part of the x86 family, which is planted firmly in the CISC camp.
And man, that x86 architecture has been around the block. Just look at this timeline. We're talking about a 50-year journey here. It kicked off with these super simple 4-bit processors back in the 70s, then it evolved to 16-bit, then 32-bit, then we hit that famous Pentium era that I'm sure a lot of you remember. And for the last 20 years or so, it's been all about 64-bit in multi-core designs. The pace of change has just been relentless.
So fast forward to today, and yeah, things can look a little confusing with all the model numbers, but the names actually tell you a whole lot if you know what to look for. Let's take Intel's new Xeon 6 processors. That first number, the 6, that's easy, 6th generation. The second number tells you the performance tier. The number after that, that's your core count. And even that last letter tells you the specific microarchitecture. It's like a secret code that packs a ton of info right into the name.
And hey, it's not just Intel. Their biggest rival, AMD, does pretty much the same thing with their EPYC server chips. The model number breaks it all down for you. The product series, how many cores it has, its performance level, and which generation it is. You can see both companies are really trying to make it easier for us to figure out what's what, just by glancing at the box.
Okay, so we've got the family history down. We know how to read the names. But what really makes one of these things more powerful than another, because I'll tell you right now, it is so much more than just one big speed number.
So what is it that really makes a CPU fast? It's not just about one number, that's for sure. It's actually a whole bunch of things working together. Let's break them down.
All right, first up, and this is a huge one, cache. Think of cache as a tiny but blazing fast stash of memory right on the CPU itself. Now, just look at this chart for a second. To grab something from that L1 cache takes, 4 nanoseconds? But to go all the way out to the main system memory? 71 nanoseconds. That is a massive difference in speed. So the more data the CPU can keep handy in its cache, the less time it spends just waiting around, and the faster your whole system feels.
And of course, we have to talk about clock speed. That's the one everyone knows, right? It's basically a base frequency times a multiplier. But here's the cool part. Modern CPUs are way smarter than just running at one fixed speed. They have technologies like Intel's Turbo Boost. This lets the processor intelligently and automatically overclock itself when it has enough cooling headroom. So for short, intense tasks, it can go way beyond its official speed rating to just power through the work.
And finally, how do we handle doing a bunch of things at once? Well, there are two main tricks. On the left, you've got multi-core. This is pretty straightforward. You're literally putting multiple, separate processor brains onto one single chip. Then on the right, you have hyperthreading. This is a really clever technology where one physical core can pretend to be two virtual cores for the operating system. It allows that single core to juggle two tasks at the same time. Now, it's not quite as powerful as having two real cores, but it gives you a huge boost in multitasking performance.
All right, we have spent a lot of time talking about the brain, but you know what? All that amazing tech is completely useless without a steady, reliable heartbeat to power it. So let's talk about the unsung hero of every server, the power supply unit, or PSU.
I know. It just looks like a boring metal box with some fans, right? But its job is absolutely 100% critical. It takes that powerful, kind of chaotic AC power coming from the wall and perfectly converts it into the stable, low-voltage DC power that all the sensitive electronics inside the server need to even function.
But it's not just about converting power. A quality PSU does so much more. It makes sure that voltage is super stable and regulated. It acts like a bodyguard, filtering out all the electrical noise and protecting all that expensive hardware from power surges. And this is so important for servers. It provides redundancy, which is key to making sure the system never, ever goes dark.
And you have to think about the scale here. We're talking about massive data centers with thousands of servers running 24/7. In that environment, a PSU can't just provide power. It has to be insanely efficient and just unbelievably reliable.
This is where efficiency ratings come in, and the big one is the 80+ standard. See, a basic power supply might waste 20% of the electricity it pulls from the wall, just turns it into heat. But if you look at a top-of-the-line titanium-rated PSU, it's over 94% efficient. Now, multiply that difference by thousands of servers, and you're talking about mind-boggling savings on the power bill, and a massive drop in waste heat that the cooling systems have to pump out.
So what about reliability? Well, the gold standard is redundancy, and the most common way to do it is N+1. The idea is simple but brilliant. You figure out the N number of power supplies you need to run the server, and then you add one extra spare. They all work together, sharing the load, but if one of them fails, bam! That +1 spare instantly picks up the slack, and the server doesn't even blink, no downtime. It's an elegant and super effective solution.
And this brings us right back to where we started, that heart analogy. It's not just us saying it. As one of our sources puts it so perfectly, the power supply is the heart of the computer system. Its whole job is to make sure that lifeblood, that clean, stable electricity, is always pumping to the brain and every other part of the body. So that really leaves us with one last big question to chew on. With things like AI and big data demanding more and more processing power and more electricity, what's next? What will the next generation of server brains and hearts even look like to keep up with all of this? It's a pretty wild thing to think about. Thanks for joining me on this deep dive.